Thank you, Hui Yin and Jill, and thank you everybody for your interest in today's talk. Well, I hope my messages today will be relatively short and straightforward, but I do have some thoughts on the last slide that will be useful to talk to the E3SM team about either today or in the follow-up meetings or discussions. The background of this presentation is that we have a SciDAC project team consisting of applied mathematicians and atmospheric scientists working on addressing time integration errors associated with E3SM's atmospheric physics parameterizations. We are interested in both errors in individual parameterizations and also errors in process coupling. In the past couple of years, one of the foci of our work has been to use strong time step sensitivity as an indicator to help us identify places in the model that can benefit from improvement. By time step sensitivity, we mean the differences in the model climate caused by running the simulation using different step sizes. For example, if we take the V1 model, use the uniform 1 degree horizontal resolution, and do two simulations, one using the default so-called physics time step of 30 minutes, and in the other simulation, proportionally reduce the various step sizes used by different parameterizations and by the dynamics by a factor of 6, then we would see, as shown on this slide here, systematically decreased cloud fraction in the subtropical areas, and related to that, significantly reduced cloud forcing. If we then compare these two simulations with observational data, we will notice that by reducing time step sizes, we will see a systematic increase in model bias, or in the other words, a degradation of model fidelity. This behavior is perhaps not surprising because our model developers have spent a lot of time and effort in tuning the default model and trying to match the model results with observation. But on the other hand, because when we reduce step size, we expect the time integration error to reduce. The degradation in model fidelity tells us that in the default model, we have a significant compensation between numerical error and some other types of error. This kind of time step sensitivity can also cause practical inconveniences. For example, in last year's ESMD E3SM PI meeting, Tang Qi gave a presentation on the V2 regionally refined model development. He noted that in the V2 RM configuration, a so-called hybrid time stepping is used, which means in order to accommodate the higher horizontal resolution in the refined region, the dynamical core uses a shortened step size, but the physics parameterizations use still the longer step size used by the default low resolution 1 degree model. Why this choice was made was because if one had decided to use also shorter step sizes for the physics parameterizations, then we would see significant changes in the atmospheric energy budget, as shown in this figure on the left from Qi, which would require retuning of the empirical parameters, which would be a very tedious work. So it would be very nice to have a model or a set of parameterizations and their coupling that were much less sensitive to step size, so that when we wanted, we could change the step sizes for the physics proportionally to what we are doing for the dynamics, or choose step sizes that we think are appropriate for the characteristic timescales that we are we want to simulate. In January this year, I gave a all-hands webinar to describe what we have been doing in this SciTech project to attribute and understand the time step sensitivities in the V1 model. Basically, what we had been doing was that we took the model and played with the various step sizes and the coupling schemes in the model, either in isolation or in combination. So this allowed us to identify which sensitivities in which geographical locations were caused by, for example, the step size used by the club and cloud microphysics subcycles, or the coupling between these subcycles and the rest of the model, or deep convection and related coupling. Since then, we have done some further decomposition of the time stepping error, looking into things related to convection, especially deep convection, shallow convection, and things around deep convection. We have done some further work and also have come up with some new hypotheses that will need to be tested in the next months. Among the many aspects we have looked into, there are two things that have turned out to be particularly interesting. So basically, we made two modifications to the process coupling in EAMv1. There, we did not change the step size for any parameterization or the dynamical core. Therefore, the computational cost is negligible. But the interesting thing is that these two modifications turned out to have very distinct signatures in different cloud regimes. For example, in the left panel, you can see that the modification number 1 has a significant impact on the subtropical marine stratocumulus clouds, while modification number 2 has a clear impact on the subtropical trade cumulus clouds. Due to the time constraint, I plan to skip the explanation what exactly we did in these two modifications and why the model is behaving this way. But these results did trigger the following questions. So if we put these two together, what is the combined effect? And more importantly, if we put these two together, can we see significantly reduced time step sensitivities in the low latitudes? In order to answer these questions, we carried out a series of 10-year simulations with prescribed climatological SST. We have two simulations that use the EAMv1 control configuration and two simulations using our revised coupling. And for each configuration, we had one simulation using the default 30-minute physics time step, and the other simulation using a reduced 5-minute time step. So in the next few slides, I will show you some results from these simulations. And for each physical quantity that I will be showing, I will present 4 panels on one slide. The upper left panel will show you the differences between two simulations that both use the EAMv1 control configuration, but using 5-minute or 30-minute time step. So basically, that will be the time step sensitivity in the V1 model. And then in the upper right panel, I will again show the time step sensitivity, but for the configuration that we have revised. And in the lower right panel, I will show the difference between two simulations using the revised versus the control model, but both using a very short 5-minute time step. For mathematicians, this panel is going to be used to answer the question whether these two configurations converge to the same solution when the step size is sufficiently refined. And for our atmospheric scientists, you can consider this panel as an answer to the question whether the revised coupling has fundamentally changed the model physics. And last but not least, I will show in the lower left corner a figure showing the differences between the revised and the control model, but both using the default 30-minute time step. So this is to ask if we just put these revisions into the model, EAMv1 model, and then use the default step sizes and parameters, what the impact will be. All the plots I will be showing are 10-year averages, and the statistically insignificant results are masked out in white. So the first quantity I wanted to show you is low cloud fraction. So, so here in the left panel, we see the time step sensitivity in the V1 control model. Again, we see significantly decreased low cloud fraction when we shorten the step size. And then on the right, in the right panel, you see the time step sensitivity after our revision. So we see substantially smaller areas with the blue color, suggesting that the time step sensitivity is indeed significantly smaller. And here in this panel, we don't see much colors at all, which tells us that when the step sizes are shortened, these two configurations converge to the same simulation. Again, so this tells us, the atmospheric scientists, that although we have revised the process coupling, we have not fundamentally changed the model physics. And so then this lower left corner shows the impact of the revision when we use the default step size. Again, we see decreases in cloud fraction. That explains why we were able to reduce the time step sensitivity. So the next quantity I wanted to show you is the net cloud forcing, so shortwave plus longwave. Here the results are similar. So in the V1 model, we have a relatively strong time step sensitivity. With our revision, we can capture a significant part of the sensitivities in the stratocumulus and the stratocumulus regimes. The revised and the control model converge to the same solution when the step sizes are sufficiently reduced. And although after our revision, there is still some time step sensitivities left. And from our previous experience, we know that these have to do with the step sizes used by Club and MG2, the subcycles, and also high clouds, especially deep convection and cloud microphysics also contribute a little bit to this signal. Now, if we change to long-wave cloud forcing, the picture is different. We know that long-wave cloud forcing is dominated by the impact from high clouds. And here in these two upper panels, you will probably see the signature of deep convection and also some of shallow convection. And the interesting thing to note is that before or after our revision, the time step sensitivity doesn't change much. And then this is further confirmed by the lower panels. And but then perhaps luckily, these two configurations still would converge to the same solution if we sufficiently refine the step size. And then at the default, with the default step size, the solutions don't differ that much either. This is not surprising because so far we have not touched much in the code that has to do with deep convection. So if then we look at the large scale precipitation, then we see a very similar picture as we saw for long wave cloud forcing. Here we know that the partitioning between large scale and convective precipitation is strongly affected by the deep convective activity. Therefore, again, it's not surprising that since we didn't touch that part a lot, with or without our revision, the model still shows similar sensitivities. So putting all those together, I would say that we made two changes in process coupling in the V1 model. When combined, they can significantly reduce time-step sensitivities in subtropical low clouds. The computational cost of these modifications is negligible, which I mentioned earlier. And here I also wanted to point out that the code changes are also very simple and non-intrusive. So for those of you who are familiar with the atmospheric model code, I will mention that the changes we made were limited in these three subroutines: TFIS-BC, TFIS-AC, and club tent cam, without anything in the detailed parameterization schemes. The remaining sensitivities we are seeing are primarily associated with deep convection and high clouds. Very recently, we started working with Guang Zhang and his team at UCSD to discuss how we can further look into the remaining time-step sensitivities, especially to investigate the impact of coupling frequency and also the closure formulation in the deep convection parameterization. And from what we have seen, it seems like ice clouds have a big impact on the remaining sensitivities in the model. It could be that once we manage to address the issues related to deep convection, because deep convection detrains moist air, we might be able to see less sensitivities associated with ice clouds already, but it could also be that we will have to further look into the stratiform cloud microphysics parameterizations to sufficiently address the remaining issues. So that was a summary of the plots and the results I have shown. So now a few thoughts that we would like to share with the E3SM team. So first of all, we think the revised coupling can significantly reduce time stepping error. So we were wondering whether the E3SM team would be interested in adopting our changes for the development of, for example, the V3 model. Have we completely addressed the time step sensitivity problem? Certainly not. So as I mentioned repeatedly, there is still issues related to deep convection and ice clouds. So because of those, the RM configuration will probably still need to continue to use the hybrid time stepping until the remaining sensitivities are addressed. But we hope that we will be able to make further progress, and if we find something useful, we certainly will report back. And thinking a little bit more generally, after exploring the time step sensitivity issue for several years, we would like to suggest that the E3SM team consider including time sensitivity testing as part of the model evaluation process. For example, as new parameterizations come in, it might be very useful to do a time step sensitivity test to see whether either the parameterizations themselves or their coupling with the rest of the model can be somehow revised to reduce the sensitivity. One comment I wanted to make is that although I showed 10-year simulations, our experience has indicated that if we do a nudged 3-month simulation, that would already be very informative. Therefore, time step sensitivity testing doesn't have to be very expensive. And thinking a little bit further down the road, we would like to suggest that it's time for the E3SM atmospheric model to rework the process ordering and coupling. We have seen multiple pieces of evidence suggesting that the current scheme is suboptimal for quite a few processes, not only involving clouds and convection, but also radiation and also some aerosol processes. And the prognostic variables affected include like humidity, temperature, clouds, aerosols, and etc. And then we have some pieces of evidence showing that the problems will likely get worse when vertical resolution is further increased. We don't know whether the E3SM team has a plan to further increase the vertical resolution to something higher than 72 levels, but we do know there are some other efforts going on, for example, under a SIDAC project exploring higher resolutions in some regions and for some processes. There, we might run into time step sensitivity issues again. And last but not least, I think the new atmospheric driver that is being developed for the V4 model can provide an excellent opportunity for reworking the process ordering. Therefore, it's probably going to be useful if we start thinking about the question already now. So that's all I had for the slides. And with that, I wanted to thank everybody for your attention. And then myself and my team would like to thank the SIDAC program for giving us this opportunity to explore this very interesting research area. Thank you.